Okay, welcome everyone. This is the week 6 webinar for the online stats class. And I don't know if you realize, but we're halfway through. So it's a 12-week class. We're in week 6, or I guess, towards the end of this week, we'll be halfway through because for 12 weeks, but we're getting at the point of close to the point of halfway through. And I thought, as always, I'll tell you about the plan for what we're going to be doing today. And as always, we'll start out with any questions you might have. Be happy to answer them. And then we're going to move on and actually use the central limit theorem in a deep way, okay, and come up with confidence intervals. That's actually a big deal. It's used a lot in the real world, especially the research world. So the idea is, you can get a sample mean. You got your sample mean. The question is, well, is that a good estimate for the population mean? Is it a bad estimate? How close are you? And what we'll do is we'll talk about a confidence interval. So we'll talk about confidence intervals for means, and we'll also talk about confidence intervals for proportions. So those are the big things to do. And then we'll also look at sample size. So we learned that in order to have a normal distribution with the central limit theorem, for the sampling distribution, if you have the means, you got to have n greater than 30. Hopefully you remember that. And if you have proportions, you have to have NP and NQ greater than 5. But there's more to it than that. So that will assure a normal distribution. What it won't assure is a sample mean that's close to the population mean, or very likely to be close to the population mean. So if you want your sample mean to be very likely to be close to the population mean, how big a sample size would you need? And that's what we're going to be talking about: sample size for means and sample size for proportions. Those are the two big things. And pretty much from now on, and actually last week too, it was all about means and proportions. And that's what we're doing the rest of this whole course. We're looking at means and proportions, except there's one chapter where we do qualitative data that's not even yes, no. And that's it. Kind of proportion, but different types. So a couple notes. This is week 6. And what's special, what's important about the number 6? Pop in the chat box. What's important about the number 6? Yeah. 6 is an even number, which means there is an exam this week. So you are required to do the exam by Sunday. I recommend by Saturday, just in case something goes wrong. And just like all the rest of them, the exam covers everything, but is more focused on week 5 and 6. So it'll be more focused on the central limit theorem and the confidence intervals than the rest, but everything is fair game. So that's a plan. And pretty much the projects were due yesterday. A lot of you actually turned them in yesterday. I always recommend a day before that. It takes me a long time to grade them, by the way. It's not like, I can just read, 20, 15-page projects in a day. Not going to happen, and just read them and write comments all throughout the whole thing. So expect it to, take me some days instead of a day. My guess is later this week I'll be done. If all goes well, that's the plan. I've already started grading them. I've got, I think, a fourth of them or so completed. And I'll do more tomorrow. I'll do more Wednesday. And if I need to, I'll do more Thursday and Friday. But I'll get them done. So the other thing is, if you're the one that submitted the project, I put a note in the things, then make sure you share the comments that I put directly onto your paper with your partners. And if you're not the one that submitted it, if your partner submitted it, then ask your partner to share with you, okay, once you get a grade. So I'll give you a comment, but all the comments, most of the comments are right in the paper. So otherwise it just, the comments wouldn't make that much sense. So that's just a note, is that, that's how I do commenting. Okay, so that is the plan. There will be a project 2. And you have a long time to do that. So you have another, 5.5 weeks before you have to finish project 2. You're not ready to start it yet, but what you are ready to do is make sure you still have partners. And if you don't, or if you weren't happy with the partner that you worked with or partners that you worked with, go find new partners. And just to note, there is a project 2 discussion board, and you can post that you're looking for a partner in the project 2 discussion board so that you can find partners. That's one thing you can do this week for the project, but that's about it. We'll talk a little tiny bit about it with confidence intervals, but really it's next week and the week after especially where we'll be ready to really fully understand the project. So that's just a note. Are there any questions about anything right now? It's a great time to ask questions. Okay, if there's no questions, let's get into confidence intervals. So I have a question that you have to answer. You don't have to tell me the truth, but if you want to lie in a reasonable number. But I might as well tell the truth. And I'm not gonna, I don't say the names, everything gets posted on YouTube, but I'm not saying who did what. And I'm gonna answer this one too, because we don't have a lot of people here. So if I don't answer, then the sample says wait, it's already too small, but it'll be even too smaller. So I want you to answer the question: how old were you when you experienced your first passionate kiss? And if you, okay. And by the way, if you've never been kissed, just give your age now. Hopefully you'll get kissed soon. Okay, so the answers are, I'll put them in numerical order. 13, 14, and 16. Okay, so one thing we can do is we can find some statistics. That's pretty easy. I can actually do the mean in my head, but the standard deviation is much harder to do in my head. So let's go to the calculator. And I'm going to go to one variable statistics calculator. It'll pop up in a minute. I'm going to put 13, comma 14, comma 16. And this is a sample of a large population. And I'm going to calculate it. So the sample mean, I'll do 1 decimal place. Okay. And that is 14.3. So that is, and it's very important that you remember the letters we use. X with a bar on top, called X bar, is 14.3. The sample standard deviation was about 1.53. Our N was 3. Oops, I wrote N, 3. And then the standard error, remember from the central limit theorem, even with a small sample size, you can still compute the standard error. That formula always works. And that is, if you remember, sigma over the square root of n. Okay, now we'll approximate that with S, 1.53, over the square root of n, and n is 3. So let's pop that in the calculator. And you get about 0.883. Any questions on that? Okay, notice this is all sample data. Okay, do you think this is a good estimate for the population of, say, Americans that have been kissed already? If you're 1 year old, you don't count. Passionate kiss, by the way. So, do you think this X bar 14.3 is a really good guess for the population mean age of first kiss? What do you think? Any thoughts? Do you think that's a really good guess? Okay, so the answer is it is our best guess, given we have a sample size of 3, that's all we've got. But the problem is the standard error is pretty high, 0.883. Does that make sense? So it turns out what you want to usually look at, and we've seen this before, it's kind of 2 standard deviations away from the mean. That's going to, be 68% likely if we had normal distribution. Does that make sense? So if we had normal distribution, then 2 standard deviations on either side would be a right. And 2 standard, in this case, it's the standard error. So 2 of those, 2 times 0.883 is about, 1.7 or so, or 1.8. And that's a huge deal, because if you go up and down, 1.7 or 8 or even 2, because we'll round it, then that's going to be like between 12 and 16 years old. Okay, now there's a big difference between 12 and 16 years old and getting your first kiss. Does that make sense? Okay, and the problem here is we had too small sample size. Is that clear so far? Okay. Any questions so far? Okay, but what we want is we want to say, well, with 95% confidence, how wide? How far away do we have to go from 14.3 to say that's what the mean age of first kiss is? Population mean. Any questions on that idea? Okay, and by the way, 95%, that actually was decided on a very long time ago, before any of us were born. I think it was in the 30s, okay, 1930s. And it was New York Times came up and decided that's what we're going to be using. And that's what everybody uses for sociology. And this is definitely a sociology kind of thing, first kiss, yeah, and psychology too. So that's what's used for that. Science is a little different sometimes. But for sociology and psychology, they almost always use 95%. Also for news, they almost always use 95%. So let me give you a little picture of what we kind of just did. Okay, so what we said is the sampling distribution is approximately normal. We assume we start with a normal distribution. In the real world, you usually can't do that, but what you can do is you can survey more than 30 people, and then you're fine. Okay, so since we had such a small sample size, we had to make that assumption in a big way. So if we have a normal distribution, this X bar is going to be our center, our best estimate. That's the center of that normal distribution. And then what we're going to do is we're going to go left and right so that the area, or the probability of being from X minus a number to X plus a number, will be 0.95 or 95%. And we need to find out what this X minus a number and the X plus a number are. It's symmetric, so it's that same number you're adding left and right. Okay, any questions on that idea? Any questions? Okay, and that's what the 95% confidence interval picture is all about. Okay, so there's an issue. Okay, besides assuming we had a normal distribution, there's a bigger problem, and that is the central limit theorem says sigma sub x bar is sigma over root n. Did we put in sigma over root n? Did we put in sigma over root n when we popped in this 1.53 over the square root of 3? Is that what we put in? Okay, the answer is we didn't. Okay, you may have thought we did, but we didn't. This is not sigma, this is S. This is a sample standard deviation. We don't know the population standard deviation, and we never will. Because in order to calculate the population standard deviation, you have to know the whole population. There's no way in the world we can get the whole population of the age of first kiss in all of America. Good luck. Does that make sense? So it turns out but if you use this S instead of sigma, which is almost always what you have to do, there's going to be an extra error. There's going to be an extra error. And because of that extra error, it turns out a different distribution than normal is used. And that distribution is called the student's t-distribution. Okay, so we're going to use what's called the student's t-distribution instead of the normal distribution. You don't have to know the details of it. It's very complex in terms of the mathematics. Even a year of calculus isn't even close to enough to understanding it, just to give you an idea. So I'm not even like going to imagine going over the math of it, but do you trust me? I hope so, that it works. And this was actually done by, I know this is like one of my favorite stories. It has everything to do with beer. Any guess on why it has something to do with beer? My guess is you have no idea. It turns out there was a statistics professor who also worked for a beer company. And he conducted a lot of statistics research for the beer company to get the best beer possible. And what he realized is that when he was doing a 95% confidence interval using the normal distribution, it wasn't right 95% of the time, which is what it should be. Okay, because you have a 95% probability of the population mean being there. And it turned out it wasn't. He was off. So he did the math and he came up with a new distribution called the student's t-distribution so that he could have better accurate estimates for his beer. Isn't that kind of cool? That's the historical story of the student's t-distribution. And I think it's because, I'm not sure, but I think it's because he worked for the company that he wasn't allowed to use his name. So he named it after his students, called it the student's t. So that's what happened. So pretty cool. So that's something we're going to be using. We're not going to be using the normal distribution for the final thing. We're going to be using this t-distribution. It turns out that if the sample size is large, the t-distribution, the student's t-distribution and the normal distribution are almost the same. If the sample size is small, like 3, they're pretty different. So there's a big error, a big difference between the student's t-distribution and the normal distribution when you have a small sample size, but not when you have a big sample size. Okay. So what we want to do is we want to talk about what it means to get this interval that goes from this x bar minus this e stands for error, by the way, to the x bar plus e. And here is the interpretation. So first thing, actually, let's find the confidence interval correctly now. And that is 13, 14, 16. So if I go ahead and go to the calculator, I'm going to go back to the calculator menu. And I actually created a calculator that finds, try this again. It's being angry. There it is. I created a calculator that does everything in our class. So which calculator do you think we're going to be using? What calculator number? It's very important that you know how to find which calculator to use, or you'll be so lost on the exams and tests and everything we do. You can't do anything without the calculator, by the way. Like just about anything for the rest of this class. So which calculator number do you think we're going to need? Based on all the words I kind of said in the last 5 minutes or 10 minutes. You can pop in the chat box. And the hint is I put them in the order at which we do things basically in the class. So 9, confidence interval for a mean with statistics. We can use that, but since we have data, let's use the data. Does that make sense? We have the 3 numbers, the answers that we got. So I'm going to use data because we have the data. If you have the data, you should use the data. So you put the data in, and again, if you remember, it was 13, 14, 16. Just a note, this example, it doesn't matter, but from other examples, it might. If you had really large numbers, like 1 million, people usually write millions with like 1, 0, 0, 0, 0, 0, 0. Don't do that. If you need to type the number 1 million is, it's 1, 0, 0, 0, 0, 0, 0. Don't put commas in. So commas are for separating the full data numbers. Okay, so that's a mistake some people make, and don't make that mistake. The confidence level, we want a 95% level. So 0.95 for the CL stands for confidence level. Okay, and it tells you what to do here, by the way, there's instructions. And hit calculate. And here is the confidence interval. Notice it's much larger than what we talked about because of the student's t-distribution, it turns out, is much wider than the normal distribution. And it's between, let's go 1 decimal, because that's kind of good for age. 10.5 and 18.1. So let's write down 10.5 and 18.1. Any questions on that? Okay. So now we can interpret it. I'm going to put in the numbers now, 10.5 and 18.1. So we can interpret the interval, and here is the interpretation. We can say with 95% confidence, we can conclude that the population mean age of first passionate kiss is between 10.5 and 18.1 years old. Notice this doesn't really tell us a whole lot because we kind of probably knew that ahead of time, somewhere in those numbers. If you want a much better estimate than this wide range, what do you think you would need to do? Any thoughts? What do you think you'd need if you wanted a better estimate that's not so wide a range? So you can say it's between these 2 numbers right here, real narrow. What do you think you'd need to do? I don't see you all jumping in. No idea? You need a bigger sample size. And that's because of this right here. Sigma over root n. And if n is larger, that makes the standard error much smaller. So if you did a sample size of 100 instead of 3, it's going to be a huge difference in terms of your confidence, in terms of your what's called the margin of error, which is how far off you're likely to be at most by using this confidence interval. Any questions on that idea? Any questions? Okay, just a note, this is, with this webinar, I don't have a lot of people here. I actually do this in my face-to-face class also, every year. I've been doing it for a long time, around 28 years. And do you think it's been the same every year? The mean age of first kiss? Think it's been pretty much the same? What do you think? Or do you think it's changed? Think there's been anything noticeable? Any thoughts? What's your guess? You can just guess. With a sample size of 3, it's not worth it. But I did it last quarter with my face-to-face class with a much larger sample size. And I do it every year. Thoughts? I don't see y'all jumping in. It's changed a lot. Okay. Turns out that the older generation kissed much earlier than the young generation. If you ask a bunch of 20-year-olds, you're gonna have a bunch of them that haven't been kissed yet. And a lot of them got kissed at 18. Whereas if you ask 60-year-olds, they got kissed at 12, 13, 14. It's been a big difference. It actually changed. Our culture is really changing. It's all kinds of things that are going on because of it. I'm not going to get into all the details, but it's really cool. And you can, again, use statistics to see relationships. What we'll learn later is correlations between something like age of first kiss and maybe crime. All kinds of different things, or lots of other things. Okay, and even more important, that's a real strong correlation, is age of first kiss and age of first child. First time you have it, how old you are when you first have your child, and how many children you have. It turns out, big thing to look at, and we've seen it. Very, very good predictor. So I'm not going to get into all the details because we only have so much time. So what does it mean to be 95% confident? So let's interpret this confidence level. Another way of saying it is 95% actually represents a probability with it the probability of. And here's what I can write. If many samples of size, for us it was 3, are taken, because we took a sample size of 3, we could do another sample size of 3 and another one and another one and another one and another one. Every time you do a sample size of 3, you're going to get a different confidence interval. Just about always. If you ask 3 different people, you get different averages, right? Okay, 95% of these confidence intervals will contain the true population mean of first passionate kiss. The other 5% will not contain the true population mean age of first passionate kiss. This is really important. So imagine you run a news company. Okay, you're in charge of CNN or something like that. So one thing you want to say is, how important is it to you that when you run an article, you're actually telling what this true statement is about the population, even though you only know about the sample? Okay, because this is how it was first decided. And what the New York Times did, which is who started it like over almost 100 years ago, is they decided that they needed to be right at least 95% of the time. And it was okay to actually falsely state something 5% of the time. Does that make sense? Any questions on that? So if that's what you're in the business of, you got to decide what percent of the time do you want to be right, and what percent of the time are you okay not being right? Okay. In medicine, do you think 95% is good enough for everything? What do you think? So if you're a doctor, do you think 95% is the right confidence level? Any thoughts? Don't see you jumping in. The answer is usually not. Because let's suppose that you're giving some medicine for acne. Got some pimples over here and here. And you want to see if there's any change in the average heart rate. Okay? If you're wrong and you end up giving a bunch of medicine where the average heart rate goes way up, you're going to kill people. So in that case, you're probably going to want to be more than 95% confident. Does that make sense? Because if there's a 5% chance you're killing someone because you're giving some little, acne polish, then that's not okay. I hope y'all agree with that, right? You don't want a big chance of someone dying because of something like acne, the medicine you gave them. Okay. On the other hand, if it was say a side effect on some major cancer treatment from stage 4 cancer, where that medicine is going to cure the patient, but maybe give a side effect, then you're maybe okay with a 90%. Because if you're wrong, then you're giving a lot of people some messy complications. But if you're right, you're saving their lives because you got it. Stage 4 cancer treatment. So it really depends on what is it that you are using it for. If it's terrible to be wrong, then you're going to want like a 99%. Okay? If it's really no big deal for being wrong, but it's really important to be able to give the information out, then a 90% is better. For our class, okay, which isn't always true of the real world, but most of the time, we're either going to use 90%, 95%, or 99%. Most of the time, that's going to work in the real world too. There are some occasions when it doesn't. But, whenever I ask you a question, it'll be one of those three, and you have to decide which is better. Okay? So if you go to a 99%, that means that you have, that's kind of the standard. Sorry, 95% is the standard. If you go to 99%, that means you're really confident about it. But there's a problem with that. What's the problem with moving to 99%? If I want to be really confident about this age of first kiss thing and go to a 99%, I can quickly in the calculator change it to 99. And instead of age 10.5 to 18.1, it's now 5.6 to 23.1. Notice all of a sudden the width of the confidence interval got really wide. So if you go to 99%, what you're doing is you're widening out the confidence interval and you're getting useless information because, of course, under 6 years old, no one has their first passionate kiss, right? You don't have puberty yet. You're not even close to puberty. And of course, the average age of first kiss is not going to be over 23 years old. Okay? Because that's like past college age for most people. Okay, for standard college age. So all of a sudden, yeah, we're really confident that it's somewhere between 5 years old and 23 years old, but that doesn't tell us anything. Do you see how that works? If I am okay with a 90% on the other hand, now it's now between, around 12 years old and 17 years old. And that's a narrower margin. Bigger chance of being wrong, but you got a better, you have a smaller margin of error there. A narrower area to say. Any questions on that? Okay, let me give you another example. If I told you that I'm, 99% confident that the weather outside tomorrow is going to be between 10 degrees Fahrenheit and 130 degrees Fahrenheit, is that going to help you at all in what you need to dress, what you need to wear? Right? Doesn't help, right? If it's somewhere between 10 and 130 degrees, who knows what you need to wear? It could be freezing, it could be hot. So having a very wide confidence interval is sometimes useless. Okay, but you're really certain of it true. But if it's useless, who cares? If I said it was 90% confident that the weather is going to be somewhere between, let's say, 70 and 75 degrees tomorrow for the high temperature, well, that's going to tell you a lot more about what to wear. Okay, for Fahrenheit, by the way. But there's a 10% chance that my interval is wrong. You see how that works? Any questions on the idea? Okay, so let's just note is I have a template. And again, you're always able to go back if you don't want to, fully take all the notes. I have a template for the conclusion of the confidence interval. So with whatever percent confidence, might be 99%, might be 95%, who knows? It can be concluded that the population mean, whatever, in our case, it was age of first kiss, is between the low number and the high number. Any questions on that? Note that this is about the population mean. Maybe I'll boldface that because it's so important. If you say sample mean, you're completely wrong. You're 100% confident about the sample mean because we know our sample mean. We have our sample, add them up, divide by the total, and there's our sample mean. We don't know the population mean, which you almost never will. Any questions on the conclusion template? Okay. I also have an interpreting the confidence level template. If many samples of, in our case, we had 3, right? 3 people, okay, are taken, then each would produce its own confidence interval. Whatever percent, 95% often, sometimes 99%, etc., of these confidence intervals will contain the true population mean, XXX, that means you got to fill it in. In this case, it would be true population mean age of first kiss, first passionate kiss. And a different XXX won't contain it. So if we use 95% for this, this will be 5%, won't contain the true population mean. Any questions on the template? Okay, it helps to have this. Just note, this is for means. This is not for proportions. Proportions are going to be a little different. So the very first thing you always want to do from now on for the rest of this entire course is say, what was the sample? What was the survey question? Was it a yes/no question? Right? Did somebody answer with yes or no? Or did someone answer with a number? We answered with a number like 13. Okay, it makes a big difference. Everything we just did is all about the quantitative data, means answering with a number. Any questions on that idea? Okay, just a note, the sample size over 30 is still required if you don't know the population distribution is normal, and you almost never do when you're talking about means. Any questions on that? Okay, that was part of the central limit theorem. If you don't have that sample size over 30, you can't do any calculations. Okay, without knowing you have a distribution as normal, so we had to assume it for ours. Okay, and I have no idea whether the distribution age of first passionate kiss is a normal distribution or not. I really have no clue at all. Might be, but I have no idea. Okay. Any questions so far? Okay, so let me get to another example. If you read it, then you already know the answer. What was the big thing that happened yesterday? I always try and do something that's new. What's the big thing about yesterday? Hopefully you all know. Yeah, yesterday was Mother's Day. Okay, did you give your mom a gift? A lot of people give a gift. All right. Did you buy the gift yesterday or the day before? Or did you buy the gift earlier than that? When did you buy your gift? Okay, so earlier. When did you buy your gift? Okay, both of you earlier. So I read an article. I always like to bring, I always like to, if I can, do an example that's, current. And yesterday was Mother's Day, so I thought, it's got to be a good one for Mother's Day, and there was no problem. I found easily just going online and finding out an article about Mother's Day that talked about confidence intervals. And so a question I have is, what percent of all Americans wait until the day before or the day of Mother's Day to pick up a gift? Okay, who waits till the last minute? Okay, what's your guess anyway? What do you think? What percent? What percent of Americans wait until the day before or the day of Mother's Day to pick up a gift? What's your guess for the percent? Let's see what your guess is. No looking it up. You're supposed to just guess. Right, it was 0% for the answers that I got from a few of you. All right, we have 50%, 20%. Let me tell you. It turns out there was a survey done by Statistica. It's a company that does surveys, and they sell it to news places. And I read it in the news place, and they said that's who did it. And they did a sample of size 400. Is 400 a large sample or a small sample? What do you think? For a question like this. Any thoughts? Okay. My guess is you would think it's large. It's actually small. Oh, we got large and small. It's actually pretty small. We're going to see in a little bit that actually it's better to have something around 1,000-ish or more. 400 is kind of small for a survey that you do with a yes/no question. Okay, it's not small for a question that's quantitative, but it is pretty small for yes/no. And just to let you know, that's the main reason. It's the main reason why for the next project, you can't ask a yes/no question, because I don't want to be the bad guy, because you need 1,000 people to ask, and that's way too much work. Okay, whereas a little over 30 is usually just fine for quantitative. The p-hat they got, which was their sample proportion, was 0.11 or 11%. So you're way off in terms of the percent. So about 11% of all Americans who buy a gift for Mother's Day buy it the day of Mother's Day or the day before Mother's Day. Okay. So the number of yes answers is n times p. So 0.11 times 400. That one I can do in my head, so you're welcome to use a calculator, but it's 44. I love 11. 11 is so easy to multiply. Any questions on that? So, oh, maybe I should write this down. That's 400 times 11, 0.11. And that's equal to 44. Any questions on that? 44 is bigger than 5, and that's important. Otherwise, we can't do anything. The number of no answers, the easiest in this case is to just say, well, if we had 44 yes answers, then we have 400. Let me write here. 400 minus 44. No answers. Does that make sense? There are 44 yeses. There are 400 people asked. Then 400 minus 44 said no. And that's 356. Okay. You're always welcome to use a calculator. You don't have to, use your brain calculator like I do. You can use a a computer calculator. Any questions on that? All right, so the next thing we need to do, Oh, and notice that those are both bigger than 5. Since they're both bigger than 5, then we're allowed to use the central limit theorem. If you can't use the central limit theorem, then we can't do anything we're doing in this class for confidence intervals. You basically give up. Okay. There are some other things to do, but that's advanced doubts. So we're not doing it. Okay. So make sure you have, big enough sample sizes. So now what I'm going to do is I'm going to go back to the calculator. Can I use the same calculator I just used? Do you think that'll work? What do you think? Can I use that calculator again? Which was number 10, sorry. Don't see y'all jumping in. The answer is absolutely not, because that's a confidence interval for a mean. And we're not talking about means. This is a yes/no survey question. Yes/no survey question, you don't get a mean. So what calculator number should I use? But you can tell me which calculator. Not a trick question. Don't see y'all jumping in. So if you have a yes/no question, it's not a mean that you get. What do? You get a proportion. So I'm going to use the confidence interval for proportion, or number 12. If you got lost on that, let me know, and I'll explain it again, but hopefully you understand it's very important you click on the right confidence interval button, because means and proportions are very different. Now it's going to ask for the sample size n. The sample size of n was 400. The number of successes. Something I don't like that much is that the statisticians use the word success for yes answer, which is sometimes really awful. Because sometimes you want to find a confidence interval for the proportion of people who die of something, die of the medicine. They call that the success if they died. So I think it's awful, but don't shoot the messenger on this one. So just let you know that they often use the word success for that. I like to use the word yes or no, the number of yes answers. And in this case, we had 44 yes answers. Confidence level, what confidence level do you want to use? I'm okay with whatever. 90, 95, or 99. Okay, 95, so 0.95. And they calculate. Okay, and we do have an approximately normal distribution, so there's our beautiful little picture. We have 95% of the data lies between these numbers, 0.079 or 0.08 and 0.14. Probably good enough, because those are, especially when you're talking about percentages, that way and it rounds nicely anyway. So 0.07 to 0.14. Okay. By the way, it'll give you a reminder our p hat was 0.11, which is good, because that's what it better be. A good check. So 0.08, sorry, 0.08 to 0.14, rounding. So the confidence level is 0.08 to 0.14. Notice that 0.11 is right in between the two. If you add them up and divide by 2, you get 0.11. It is the midpoint, which it needs to be because of the picture, because that is what we set as the mean for the normal distribution. So the left and right should be the same distance from the mean. Any questions on that idea? Okay, the margin of error is going to be the distance from the center to the edge. Okay, so the distance from the center to the edge, you can go 0.14 minus 0.11. The center was 0.11, the high point was 0.14, and subtract. You could also do 0.11 minus 0.08. You'll get the same number. And you get 0.03. And that's your margin of error, or 3%. Okay, if you're off by 3%, that's pretty good, don't you think? That means your error is not too big. I mean, you may want to be within 1%. They need a bigger sample size, by the way. Okay, so interpret the confidence interval. We say with 95% confidence, we can conclude that the population proportion of all adult Americans that wait until the day before or the day of Mother's Day to pick up a gift is between 0.08 and 0.14. Any questions on that? Notice I bold-faced the word all, so I'll just say it loud in case you don't see bold. So the proportion of all adult Americans. If I bold-face it or yell it loudly, what does that tell you? You've done this before in our class. Yeah, it's important. And if you don't directly refer to the population or all, you will lose points on the exam, on the discussion post-assignment. So make sure, take notes now that that needs to be there. Okay, it's a common place people lose points. Okay, and when we talked about the mean, by the way, we use the word, wait here, population. Okay, it's another way of saying all. Okay. The other way of saying the same thing, I like to kind of look at it in two ways, is with 95% confidence, we can conclude that between 8% and 14% of all adult Americans wait until the day before or the day after Mother's Day to pick up a gift. Okay, some people like using percents instead of decimals. When you're telling it, especially the general public, a lot of people understand percents better than proportions. So it's kind of two ways of saying the same thing. The second way is definitely better for those who are not as educated. Any questions? Okay, let's interpret the confidence level. It's very similar to what we did before. If many groups of 400 adult Americans are surveyed, then each group will result in its own confidence interval. 95% of these confidence intervals will contain the true population proportion of all Americans that wait until the day before the day of Mother's Day to pick up a gift. Okay. So I like to think about, you do a confidence interval and you do a bunch of them. That's your job. 95% of the time, you do your job right. 5% you do it wrong. It doesn't mean you're a bad worker. It just means 95% you got lucky and it was right. 5% you got unlucky and it was wrong. Does that, any questions? Any questions on this idea and how I kind of use the template? I do take a lot of points off, by the way, if the question is about proportion and you write about means, or vice versa. So you need to make sure that you have that down. to really know. So if all you do is you copy and paste the template and don't pay attention to the word proportion and mean, then there's gonna be a lot of points lost. So don't just copy and paste without thinking. Any questions at all on this example? Okay. And I like using, real examples, and this was in the news. I think it was a day or two ago where it was in the news. Pick up that easily. I can always find stuff that is important, that's relevant. And that's, to me, that's why I think this class is so important, is that everything we do is relevant. Okay, it's not, when am I ever going to use this? It's used all the time. It allows you to be able to read the news and be able to look at it and say, hey, are they doing it right or not? What did they do? And to understand it, understand the details of how they did things. Any questions on that? All right, now we're going to do a next thought, and that is in your planning stage, how big a sample size do you need to do to plan for in order to have good data? That's really important, because in the real world, the hardest part about conducting a full study and doing the full analysis is actually collecting the data. Okay, if you had to ask 400 people, and using good, somewhat non-biased sampling, it's going to take a lot of work to get those 400 people. Okay, does that make sense? Okay, especially if you want to really have unbiased data. And I want to mention that if you have biased data, the confidence interval is worthless. And pretty much if you have biased data, everything we do in this class is worthless. So everything here assumes that you don't have bias. Okay, if it's very slight bias, that's not so terrible. But if you just do some kind of convenience sampling and it's really biased, then it's awful. Any questions on that? Okay, so here was a formula we had, and that was from the central limit theorem. Sigma sub x bar is equal to sigma over root n. Do you remember that little formula? Okay, that wasn't a biggie. We're going to use this a lot. So if we want to find out how big a sample size we need, we want to say, how big n do you need? Okay, so what you got to do is say, well, if you know sigma, and you know what you want for sigma sub x bar, you could do some very basic algebra and find n. Any questions on that idea? Okay, so just a note, E is equal to Z times sigma sub x bar. Okay? Where Z is the Z-score. Okay, for that normal distribution. So for example, 95%, if you remember from the empirical rule, 95% is how many standard deviations from the mean? Gets you a 95% probability. Remember? How many standard deviations from the mean will give you a 95% probability? You remember? That was the empirical rule. I know it was some weeks ago. That was 2 standard deviations. It's 2 weeks ago, too. Just coincidentally. Let me give you a heads up. There's a small chance that that this is going to stop immediately, this webinar. Any guess on why? I don't know if you can hear. No guess? We're getting really strong hailstorm right now. Yeah, it's not solar flares. We're getting a really strong hailstorm. It is pounding outside. So hopefully we don't lose internet. But if we do, I apologize, but I can't do anything about it. So let's hope. Yeah, it is just damn. I don't know if you're in Tahoe, but if you are, then you're getting it too, probably. Okay, so hopefully it won't happen. Okay, so we can say Z is like that 2 if it was 95%. Okay, it turns out to 2 decimal places, it's 1.96. That's kind of the standard that most people use, which is close to 2. Okay, and so that was if you want 2 standard deviations. If you want 95%, if you want 99%, it's more. If you want 90%, it's 1.645. I mean, different Z's happen, and you can use a calculator to find them. So we can say that N, by solving this algebraically, is equal to Z sigma over E quantity squared. That's going to be the formula. Any questions on this so far? Okay, so let me give you an example. Let's suppose we wanted to find a 95% confidence interval for the population mean hourly wages of nurses in California. Okay. Based on a preliminary study, and that's what you usually do, you do a small little sample so you can get an estimate of the standard deviation. We're going to assume the standard deviation is $25 an hour. Okay, so in the real world, that's what you often do is you do a small sample, find the standard deviation of the small sample, you're going to use that as a best estimate for the standard deviation. Okay, you want a margin of error no more than 50 cents. How many nurses must you survey? Asking them how much do they make? Okay. How much do you make per hour? So how do we do this? Okay, one way of doing it is you can say, well, if we own a 95% confidence interval, Z is 1.96. That's what I just told you. Sigma is 25. So you do 1.96 times 25, divided by the margin of error, which is 0.5. Do that and square it. And that will give you N. Okay, and that'll always work, but there's an easier way. Any guess on the easier way? Guess on what the easier might be? All right, there's an easier way. Now you might be able to guess. What's the easier way? Let's see y'all jumping in. The easier way is to use number 11, sample size for a mean. Right? This is a mean. We're talking about the survey question is how much do you make an hour? Somebody, might say, $85 an hour, and that's a number, not yes or no. Is that clear? So that means we have a mean and we want a sample size. So because we want a sample size, we do sample size for mean. And then it'll ask, what is sigma? Sigma, if you remember, was 25. Margin of error was 0.5. Confidence level, we wanted a 95% confidence level. And hit calculate. And you get 9,604. Okay. By the way, that would take a lot of work. You see, none of this like, oh, you need something over 30. No. If you want a really good estimate with only a 50-cent difference, then you're going to have to survey a whole lot of people. What if you were okay instead of a 50 cent? What if you were okay with, say, a $2 difference? Any guess what would happen to N? Just thought. Wouldn't be 9604 anymore. Any guess? If I plug in 2 instead of 0.5, let's see, I'll jump it in. Then you have to survey 601, a lot easier. So making that margin of error really narrow takes a lot of work. You see how that works? Okay. You can't change sigma. Okay. There's no way you can change the population standard deviation of how much nurses make. Okay. I don't have that power. So that's never going to be able to change. Margin of error, that's something that you decide when you're creating a study. Confidence level, that's also something you can decide. Okay, and again, 90%, 95, and 99 is what almost everyone uses. Nobody uses like a 10% level of confidence. That never happens. Okay. Any questions on this? Okay, so that's what we need. Any questions at all on the idea of finding how big a sample size you need if you want your margin of error small enough with a certain confidence level? Any questions on that so far? Okay, we could do the same thing. We could do the same thing for a proportion. The formula will be different, as you might guess. The formula will be different. But you can definitely do that. It turns out that if you can do a confidence interval for a population mean, and you want to figure out how big a sample size you need, you have to have an estimate for the standard deviation. Without an estimate for the standard deviation, you can't get the calculation done. Okay? But for a proportion, it turns out you still can, even if you have no clue what the proportion really is. You could still get an estimate. Any questions on that idea? So here's an example. Suppose you want to find a 99% confidence interval for the population of cars in the United States that are electric vehicles. Okay. That's definitely a study people are doing. Okay. And by the way, next year will be different. Every year it's a little different, right? Okay. You want a margin of error of no more than 3%. How many cars must you look at? All right. It turns out there's two ways of doing it. One way is you write out the formula and you do a whole lot of really hard math, including calculus. Okay. And this class, we don't do calculus. So we're not doing it that way. Any guess on the other way you do it? Any thoughts? No ideas? Can we use this calculator? What do you think? Let me know. Can you use it? You can put in the chat box yes or no. Can we use this? You jumping in. The answer, this is the sample size for a mean calculator. It has a standard deviation. There's no such thing as a standard deviation for just a yes/no survey question. You have a standard error, but not a standard deviation. So this will not work. This calculator does not work. On the other hand, if I go back to the calculator menu, what calculator can I use? What number? Here's a cool coincidence. Let's see, y'all jumping in. Not a trick question, should be obvious. We want a sample size. We have a yes, no survey question. Yeah, 13. And the coincidence is, what's today? May 13th. Total coincidence. So number 13 is sample size for proportion. And that's what we have. We want a sample size and it's a yes, no survey question. And it gives you a choice. Do you have an estimate for P or do you not have an estimate for P? Have an estimate for P, no estimate for P. In this case, we have no idea. It didn't give you anything about an estimate for proportion. All we're given is the margin of error that we want and the confidence level that we want. 3% margin of error, 99% confidence interval. So no estimate for P. 3% is 0.03. Confidence level is 0.99. And I hit calculate N. 1,844. Any questions on that? Would that be a lot of work? Okay, that'd be a lot of work to try and survey 1,844 people asking what kind of car they have. That's a huge amount of work. This is why it's so important in the real world to get this right. Because if you say 1844 and you really only needed 500, you're doing a lot more work than you needed to. You're totally wasting your time. On the other hand, if you said 1844 and you really needed 5,000, then you're going to do the whole planning and funding and all that and do this project at survey 1844, have no more time because you got to, you got this deadline. And then you have a terrible confidence interval that is way too wide because you screwed up. So this is one of those where in the real world, it's a disaster if you choose your wrong sample size. Okay, then there's a part B. That for now. So 1844 is what we just got. Okay, you look at last year's data, and only 2.2% of all cars were electric vehicles. Okay. How many cars would you need to look at for the 99% confidence interval? So can we use this calculator? What do you think? Okay, the answer is yes. We still want a sample size for a proportion. But what's changed is we now have an estimate for P. So now I have to click have an estimate for P. And now it asks for the estimate. And our estimate was 2.2%. And that is 0.022. So it is important you know how to take percents and turn them into decimals. And now when I hit submit, I need a much smaller sample size. So having an estimate often helps a lot, especially if your estimate is a very small percent or a very large percent. Okay, it turns out if the estimate's 50%, you get the same thing as not having an estimate. I'm not going to get into the math on that. Okay, any questions at all on this example? I do want to let you know that when I coded this calculator, especially the sample size, actually professors at some other colleges got mad at me. Because they said you're making it too easy for the students. Because they wanted them to do all the math and the algebra and all that. But I decided to do the code. So hopefully you're not mad that it's too easy. But that's what some of the professors told me, that I want them to do all the detail of the algebra part. But I'm okay if you use a calculator. Any questions on this example on finding a sample size when you have an estimate for the proportion? Okay, and it's just a guess. Doesn't mean you know the proportion. It just means you have, sometimes you do a study. One is you can look at last year and you're trying to look at this year and say, maybe things haven't changed much. Another estimate would be, maybe you're gonna ask 100 people, and if 5 of them had an EV, you'll use 5% as your estimate, and then use that and see how many more you're now gonna have to ask. So there's different ways of getting estimate. One is do a small sample first to just do an estimate, and then enlarge it. And the other is do research on something somewhat similar and use that as your estimate. Any questions at all on finding the sample size for a proportion or for a mean, and for a proportion with an estimate versus without an estimate? Any questions on that? All right, if there aren't, then it's time for the secret word. And the secret word is population. Because as I mentioned, if you're looking at means and you don't have that word population there, I will take off points. So that's an important word. Okay, and you can do proportion too. Population proportion is allowed. Okay, so that is important, that you have to, when you're doing a confidence interval, you're doing a confidence interval for the population, mean or proportion. So that's the secret word. And that's about it. It's a bit shorter than usual. One thing is you're probably a bit tired from the project. Nice to have a little bit of break. And the other biggie is you got the exam this week. So there's, it's a big week because of the exam. So I am going to say goodbye to those who are watching this on YouTube.